Okay, so we talked about how some isotopes of some atoms are radioactive. And so here's an example of a block of carbon. Carbon is mostly carbon-12. And there is actually some carbon-13. And there's a very small amount of carbon-14. And carbon-14 is radioactive and undergoes beta emission as shown. Let's say this little carbon atom right here, this carbon-14, disintegrated. Okay, so a beta particle flies out. The particle flies out, and now there's one less carbon-14 in there that can shoot a particle out. So if these things were shooting out from individual ones at a random time, and I looked now, I would see so many counts per second. If I waited, the number of carbon-14s that are still there is now smaller. So I would expect less of them to be disintegrating at any point in time because there's just less to choose from. The individual disintegrations are completely random. I don't know which of these carbons is going to disintegrate, and I can't even influence it. But if there's a large enough sample, then there's always somebody that's disintegrating, and beta particles would be flying out almost all the time, or all the time. So they've discovered that carbon-14, which is produced in the atmosphere, gets into the carbon chain. And carbon, so you have CO2 in the atmosphere, it's absorbed by plants, and then the plants make carbon, which is food, and then we eat the plants, or we eat animals that eat the plants, and eventually these carbon atoms get inside us. And so if carbon atoms get inside us, we have some of the atoms that are carbon-14. So that means we actually have radioactive carbon-14 in us. As it disintegrates and becomes nitrogen, that carbon is now not carbon anymore. That whatever it was in is now destroyed, and our body recycles and puts new carbons in. So we have kind of an average amount of carbon-14 in us in all the time. They've measured it over years and found that it's about 14, you get about 14 disintegrations per minute per gram of carbon-14. So if you had a 1 kilogram or 1,000 grams of carbon-14, you should expect about 14,000 disintegrations per minute. Okay? Now that's happening, but as that carbon-14 is consumed or turned into nitrogen, we would expect that number to go down if it wasn't for the fact that we keep recycling new carbon in. But when an object dies, the amount of carbon, the recycling process stops. And so there's a starting point that will finally start to get less because carbon is not recycled in. We can use this fact to figure out how old something is if we know some things about carbon-14. One thing we know is if you have a sample of carbon-14 and you measure its activity, which is how much radiation is flying out, usually in counts per second, and I do that as a function of time, I can find that if there's some starting amount, that later there should be less radiation flying out per second because there are less carbon-14s in the sample because they've turned into nitrogen. If I measure the amount of time for that to go down to half of what it was, it turns out that time for carbon-14 is 5,730 years. If I measure it now, I get half the activity of when it started. Okay? So if this was 14,000 at the start, this would now be 7,000. If I wait another 5,730 years, which is about that long, this number here should be half again. And so these things where the rate, or how fast they're coming out, because that's kind of a rate, how fast they're coming out depends on how many are still there. Oftentimes in nature, they call that exponential decay. There's a mathematics that seems to match it. And it has to do with this number, e to the x. Now, I don't know how much we do in e to the x in our school. I know they do it in calculus. What is e? Well, if I said pi, you would know that's 3.1415 and a number that goes on forever. Could I have pi squared? Sure. Now it'd be hard to do because I'd have to have infinitely large parenthesis out there with a squared at the end. Okay. So can you take a square of a number that never repeats? Well, you can, or at least you can estimate it. And your calculator, if you did pi squared, would estimate it. Turns out e is another number like pi that comes in nature. It comes from this situation. It's about, let's see, I can check on my calculator. I can find what e is if I put in e to the first power, because there's an e to the x button on your calculator. The e to the x button should be right by the ln x button, which is called the natural log. The natural exponential and natural log are related. If I do second e to the x and put a 1 in there, I get e to the first power is 2.718281828, and it goes on forever. So e is some number that comes from some natural math, just like pi comes from the ratio of the circumference to the diameter of a circle. Okay, I can't explain more than that of how this decay has e in it, but it just seems like things that exponentially decay or exponentially grow, like bacteria, the mathematics seems to have e to the x in it. And if you graph this and find the equation, what would the equation look like? Well, the equation would be the activity later is some function of how much time there has been. So what is that? And why would that be useful? Well, that means if I knew the activity now, then maybe I could figure out how long it's been decaying, which we could use for carbon-14 dating. Okay? So how would I do that? Well, if you do the math of this, you get an equation that looks like this. The activity now is activity at time equals 0, e to the negative 0.693 over the half-life times the number of years that it's been decaying. Now, where that comes from, I'm not going to worry too much about for our class, but there's a formula that says if you tell me the half-life and the number of years that's been decaying and the starting amount, I'll tell you how much activity or how much radiation is coming out at some later time. How would we use that in our carbon-14 example? Well, we could say that if I measured the activity now was, I don't know, 7,000 counts per minute. If I knew the beginning activity was 14,000 counts per minute, at least that's my assumption, and I know this formula says e to the negative 0.693, and I know the half-life, which I've got from experiment. I put that right here, 5730 years, and I multiply by some length of time t. If I do this math, I'll find out that the time for the activity to be cut in half is 5,730 years. Okay? Solving for t. So the question is, how do you solve for t in an equation like that? So let's say I had this. Here's the equation. A equals the beginning activity, e to the negative 0.693 over 5730 times t. So how do I, if I said, here's the sample, and it started off with, we're going to assume it's a 1 kilogram sample, so it had an activity of 14,000 disintegrations per minute. Disintegrations per minute. Okay? If I assumed that, and now it was, I look at it, and it's now down to 10,000 disintegrations per minute. Well, what do I do? If it had made it to 7,000, which is half, I would have said, oh, that's been 5,730 years. But it hasn't been that many years since it stopped recycling the carbon, because it's only down to 10,000. So what do? Well, I'm going to plug these numbers in, then I have to solve for t. That's going to look like this. 10,000 counts per minute, or disintegrations per minute is what I have now. I'm assuming that way back when it died, there was 14,000 counts per minute per gram. And I have e to the negative 0.693 over 5730 times t. And I have to solve for t. Now, when you're solving for a letter, that should make you think, oh, that's an algebra class. So I think the first thing I'll do is divide both sides by 14,000. So 10,000 divided by 14,000 comes out 0.714. So I have 0.714 equals e to the negative, and I'll go ahead and divide this out to see what that is. 0.693 divided by 5730 comes out 1.209 times 10 to the minus fourth times t. So I have to solve for t somehow. So how do you do that? Well, I have to get t back on the line that is not up in the exponent. Now your math teacher should have taught you in Algebra 2, although Algebra 2 is not a prerequisite, how to do equations where the variable is up in the exponent. So if I had 4 equals 10 to the x, in math you learn, to get x back down the command line, you do this thing called log of both sides. And it kind of cancels that out, and I get x is log 4. That means log base 10. You'll notice on your calculator that the log button is there, and the second function is 10 to the x, because those are the inverse functions. Well, also on your calculator, you'll see that there's a button that says ln, and right above it is e to the x. I'm not canceling it out, but if I want to get this number down on the command line, I need to get it out of the exponent. So I'm going to do natural log of both sides. Okay, natural log of both sides cancels the e. So I get natural log of 0.714, which I just do on my calculator. So natural log of natural log of 0.714 comes out negative 0.336 equals now negative 1.209 times 10 to the minus 4th, all that times t, and I've got the variable down on the command line. Now I'll divide by that negative 1.209, divided by negative 1.209, enter exponent, negative 4, and I get t equals 2,786 years. Does that make any sense? Well, yeah, we knew that it would have had to go, to get down to 7,000 counts per minute, would have taken 5,700 years. It only went down to 10,000, so that took less than one half-life. That's the math for how you calculate how long something has been decaying once the carbon has stopped being recycled. That's called carbon-14 dating.